good to go. Let's do this.
All right. All right. Welcome everyone to the introduction to quantum computing and quantum mechanics. My name is Jaimil. I'll try to keep it as simple as possible. I don't want to get you guys intimidated by all of it. So let's get into it. So here's a little bit about me first. My name is Jaimil. I'm a grade 12 student at North Park Secondary School. I'm going to this University of Waterloo, for computer science this fall. And I've done a few projects in quantum computing. I have done a year-long course from IBM in quantum computing, and I probably will be going into the field later in my career. Yeah, so that's a little bit about me. I love coding as well. I don't want to be mentioned that. I've done a bunch of hackathons and built quite a few projects. So, yeah.
Go for your project.
Hello? Oh. All right. So, what is quantum computing? Well, basically, it's the same thing as classical computing, but it's built fundamentally different. It's going to be a new era of computers and processing. And I'm sure you guys have all seen or heard the hype around it that like Google, IBM, they're all like, oh, quantum supremacy, or, it's getting very nice now. Basically what's happening is quantum computers, they allow for a lot more processing power, which makes it easier to do or solve very, very hard problems. Just to give you a statistic, one of these problems would take a regular computer 1,000 years or 10,000 years, but for a quantum computer to do that problem, it would take mere minutes, or I think 120 seconds. You can research it, but that's that specific type of problem, right? So they're definitely giving a lot more processing power. But how do they do that? To put it simply, computers, they only understand ones and zeros, okay? They're built on electricity, right? Or transistors. Basically, there's a law called Moore's Law, I believe it is, that every year computing power doubles. And how does computing power double? They double the amount of transistors in your processor. So a transistor is basically like a switch. You see that switch back there? It can either be on or it can be off. On means 1, just off means 0. And that's how computers basically do everything. But the difference is for quantum computers, they use qubits, which allow for ones or zeros, like on or off, but also anywhere in between. So what does this mean? It could be 70% 1, it could be 30% 0. It allows for probabilities. So it's not exactly just 1 or just 0. It allows for a lot more space in between.
Right.
And so that's how they're fundamentally different. They're built in a completely new way that's never been seen before. And that's why they allow for a lot of different types of, I guess you could say, solutions to problems. They're also cloud-based, which means that anyone, anywhere in the world can use it. Because IBM has actually, will be actually coding on a quantum computer today, very soon. But IBM has set up a cloud-based system, which means you can open up your computer and access an IBM quantum computer from your home and use it to do something. So that's very cool, and it's accessible to anyone. It's for free. And like I mentioned, the increased amount of processing power leads to a lot more saving in time and optimization for a lot of different things. So just quickly to give a brief history, it started off in 1980s when Richard Feynman, he was a scientist who was the father of quantum computing, or quantum mechanics. He was a big researcher in that field. And he said, if we could make computers built off of quantum physics as opposed to just regular physics, then we can achieve anything. So what happened is David Deutsch, who is known as the father of quantum computing, in 1985, he coined the term called universal quantum computers, and he started doing research in that. And as time passes, different people got into the field and they started researching more and more on what you could do with quantum computing. So we have Shor. These are all famous researchers. There's Shor, who developed Shor's algorithm. There's Grover, who developed Grover's algorithm, and Lloyd. There's all these different researchers, and they're very useful algorithms for doing different things. And recently, there's been like companies getting involved in the field as well, like IBM, D-Wave. I think Google is also in it. Microsoft has it, and it's getting very popular. Even some universities have it. And IBM hopes to get, it's made a plan to get, I think, 1,000 qubits. Right now, it's only at like 100 qubits or something, but it hopes to get 1,000 in the next 5 years, which means it will just increase and increase and increase in terms of potential, right? Just in case anyone doesn't know what quantum is related to, remember how I was talking about transistors or on and off switches? They go based on electricity. So if electricity is passing through, the switch will be on. If it's not passing through, the switch will be off. In a quantum computer, however, it uses quantum mechanics, which are different. It looks at particles, and it looks to see which position they're in, I guess you could say. For example, they could be up or down, or they could be in between, which is called superposition, which is what we'll be making use of. But that's just a little brief history. So don't get intimidated. This is what they look like right now. But even regular computers looked like this in the past. They would take up the space of an entire room. If you look at the computer that was used to, I think, make the calculations to go to the moon, it was like massive, right? But 20, 30 years later, we have laptops, we have phones, right? So quantum computers right now take up the space of an entire room, but soon I think we'll get to a point where they can be used in other spots. So how do they work? Here's just a simple diagram. We have the quantum computing here. It's basically where all the electricity flows through and the conducting lines are. And the main thing is that for qubits to achieve superposition, which is what allows them to get like the probabilities instead of just 1 and 0, it has to be in a very, very cold environment. So it has to have, I think, close to freezing point or 0 Kelvin, which is very, very cold. And that's why not everyone can just access them directly. And that's why they have refrigerators. And here we have the actual processor. And basically what happens is the data gets converted so that regular computers can use it. So they're not actually entire computers. They're more like processors that we can use with our own computer using IBM Qiskit and other networks. So future prospects and industry applications. This is a very, very new field, so there's a lot of job opportunities. In fact, there's high school internships, there's university level internships, and you don't need you don't need to have a PhD to do it, basically, is what I'm trying to say. It's for all experience levels. And this industry can be applied to anything, really, because quantum computing is really helpful in chemistry, for example, where you need to find which proteins work the best. And there's like 1,000 different possibilities, but you need to find the one best one. So it's really helpful in that. It's helpful in physics, computing, machine learning. There's also quantum machine learning, which is a new field. Finance in stocks and all that, and so much more. And in fact, it's already being used by Microsoft. It's being used by Volkswagen for, I think, their travel system to calculate about traffic. Or something like that. JP Morgan and Chase, which is a financial company, which deals with stocks and all that. So that's finance. And it's expanding. It's like ever expanding. And since it's still new, if you get in early, it's the best time because you're there at the start. You know everyone. You know what you're doing. And then as soon as it develops, you've already been there. So it's like founding Facebook, right? When it started, it was very small, but now it's massive, right? And it's also providing a very nice social community. But yeah, that's a little bit about quantum computing in the most basic sense. And today, we're going to make a quantum computing algorithm. Just really simply, okay? Don't worry. I understand that some of you may not know too much about coding, but basically what you're going, like this is the interactive part where you can follow along if you'd like to. I sent this link in the chat for this workshop, and you can sign up using Google or anything, and once you sign in, it will allow you to see this page. It's also free, so don't worry, you can sign up right now. It takes a couple seconds, and I'll give it a minute before I start. But yeah. Does anyone have any questions, by the way? You can ask them at any point. Feel free to unmute or ask them at the end or drop them in the chat. We can see whenever. But I guess I'll start with this. So this is IBM's quantum computing framework, where you can build different algorithms, circuits, and programs to do different things, and actually run them on actual quantum computers around the world. For example, there's IBM Q, Jakarta, Manila, there's a few more, but yeah. So we have the IBM Quantum Lab, and we have the Quantum Composer. The Quantum Lab deals a lot more with coding based, or like the hard coded, whereas Quantum Composer is also for, it's more visual for us, I guess you could say today. There's also something called IBM Qiskit Metal, which is used for hardware, but we won't be going into that today. So we'll make a simple algorithm today in Quantum Composer, so make sure you hit that. This is what we're making today. I know it looks very, very complicated, I guess, to you guys, but we're just going to hit new file first, and I'll explain what's going on here. Okay. So this is your composer, and basically here you have the name of your circuit. I'm going to call it Grover's search algorithm. And hit enter, and here you have a bunch of different blocks you can use. These blocks, most of them are actually called gates, and how quantum computing works is it's very math heavy. So you have these things called matrices, and when you apply these gates to those matrices, the matrices change, and they show different values in the most basic sense. So let's say you have a probability, right? And you put a gate to it, it will alter that probability for more useful information, I guess you could say. So what we'll be doing is basically putting a bunch of gates together to try and get what we're looking for. So the example I'm going to give today is called Grover's search algorithm. And the thing about, I don't know if you guys know, but in coding, or anywhere really, there's a thing called search algorithms. So let's say you have a long, or let's make it even more basic. Let's say you have a long line of people in a grocery line, and you went to get something. You're looking for your mom or dad. So how would you find your mom or dad? You would probably go one by one looking at each person until you see your mom or dad, right? That's how regular computers work. What they do is they can, at the most, what they'll do is they'll look at each and every person and see if it matches what they're looking for, and then it will accept that. So at the most, let's put a letter to it, n. It takes n number of tests. So let's say there's 20 people in the line. At the very hardest, it would take 20 tries to find your person. Quantum computing makes that so much simpler. It looks at the entire group together and finds the most probable or most possible outcome and outputs that. So it will see your mom or dad as the most probable one, and it will output that saying, here's where you need to go. And the reason why this is so much faster is because it can look at multiple things at once. It's looking at probability. It's not looking at yes or no. Like, it's not going to go through each one and confirm it. It's going to go through the entire thing, the entire line, and try to find the most possible one. Oh, that was Siri. Sorry. But yes, so what we're going to do today is look at how to find one of, I guess you could say, 4 most possible outcomes. I'm just gonna hit trash can here. So down here, you see probabilities, right? 100%, 0, 20, 40, etc. So here at the bottom, we have 4 different options, right? And we have 0, 0, 0. Okay? So we have 1, 2, 3, and 4. Let's say we're looking for 1, which is 0, 0. Okay? In a list, in that list. And you want to make sure that you get that just from this algorithm instead of having to look through each and every one. So in the most basic sense, this is called a Grover search algorithm, which is why it's so popular. This makes database like handling much faster and easier in the real world. But basically, we have these things called qubits, like I mentioned. And when you just have them regularly, they're in the 0 position, so they can be 0. They're not 1, they're not a probability, they're 100% 0.
Sorry to interrupt, but where do you get Grover's search algorithm from?
We'll be making it. We'll be making it.
Okay.
Grover's search algorithm it's been developed by Grover, and they've made it multiple times over and over on IBM and their tutorials and whatnot. You can actually put my presentation link, but it has a few links that you can access. But we'll make that right now. So on the right side here, I don't know if you guys see it, but it's called it's Qiskit, which is the code framework, which you can see how if I put something on, right, it will automatically change here. It added this, which means that it's basically showing you the code for this, whatever you're doing here. So I'm not sure if you noticed that, but at the start, they're in 0 position, right? So to make them into a probability, like 50-50, like you don't know whether it's 0 or 1, there's something called an H gate, which is the Hadamard gate. We're just going to grab that and drop them on to each line. This is qubit 1, or qubit 0 and qubit 1. So what this does is it sets them both into something called superposition, which is probability in the most basic sense. And I'm not really going to go into the gates too in depth because I know that you guys may be beginners and it might be very intimidating. So we'll just do a little bit of drag and drop. So as you can see here, when I added it to the first one, before it was just 0, 0, right? So when I add it to the first one, it becomes 50-50. So this second number here, right, at the bottom, I don't know if you can see me highlighting it. It represents the first qubit. So is it 0 or is it 1, right? So it's a 50% chance that it's 0 and there's a 50% chance that it's 1. But what about these? There's no chance yet, right? That's because as of right now, the second qubit is 0. And these look at 1 for the second qubit. And it's not going to be 1 unless we add another gate. And now it's all split equally, 25, 25, 25, 25. Because there's a 50% chance that this is 1 or 0. There's 50% chance that this is 1 or 0. But yes, that's how quantum computing works in the most basic sense. I don't want to get into probabilities or like vectors, state vectors and all that. But next thing we're going to do is add a Z gate, which is basically it flips the sign. So if it was in the positive, this here is the block sphere, which shows probability in 3D. It's just cool to see. So when we add a Z gate, it flips the sign from positive to negative, so it goes bottom, like if you've seen on a graph. And we're going to do that for both of them. And then we're going to add a phase gate. Basically what this does is it applies a phase to the qubit. And it makes it easier to calculate things. So now you can see it's split evenly, right? All over.
I don't have this. I don't have the sphere there for the Q sphere.
You don't have a sphere? That's fine if you don't. It's just a visualization. Does it say state vector?
No, I'm on Q sphere.
Okay. It just might not show if you. Let's see. Yeah, it just might not show for some reason then. That's fine. It's not going to be very important for the actual run. But yes, I'll keep going. There's something called a barrier that we're just going to add. It's just like dividing it up so that we can visualize it. And there's some science behind it, which you might not need to know right now. And this is the first part, which puts them into superposition and adds them up so we can do what we want. And now, what this does is it looks for the most probable one. So when we're doing this search, we're looking for the answer to be 0, 0. So we want it to always show 0 as our outcome. So let's say your mom or dad is first in line. We want to always find them first in line in this algorithm. And that's why this is a part of it. And next up we have more Z gates to do some more flipping. And then we have another phase gate, and another H gate. Again, there's a lot of math behind this, which is why the probability works properly. See, if you put this at the end, you'll see that 0, 0 has 100 probability to always show up as 0. So this basically, if we put this in, and here we have a measurement block, which basically at the end of all the processing, you need to measure what you got built. So you're just going to put that on each line. So once you have this, you can actually click setup and run, and it's going to show you this here. Just check the time real quick. It's getting very close. I mean, I have to the project.
Note, I just wanted to bring up, we only have roughly 4 to 5 minutes left, but yeah, I think we'll be able to wrap up by then.
Okay, so I'll just show this. So this is called a simulator, but there's also like actual quantum computers that you can see here and you can run them on. So I'm just going to click this one and just run it. And when you click run, it will show up on the left side here called jobs, and you'll see it here. This is one I just did, and you'll see that the probability for 0 is 100%. And that's basically.
Can you show us how to run it again?
Yeah. So you click setup and run at the top right, and on the left side, just it's probably already picked, but just pick simulator at the bottom, and hit run, and it will just run by itself. And to see it, it's on the left. Really quick, 1 minute run. Here's the Grover's algorithm in code. Not very important. You import some different things and you make a few, lines of code and you get it. Here's an example of the party we want to call 4 people, but one of them doesn't get along with the other. Then you want to find all the possibilities that you can do. So you can invite, 1, 2, and 3, but you can't invite 4, for example, right? This is what I wanted to show, but I guess we don't have time. I'll quickly just go to my presentation. But basically some implementations are you can use it for satisfiability problems, which is like if you're looking for certain possibilities or outcomes, or for example, Sudoku, which is like a problem. I don't know if you guys have done it before, but each row and each column can't have the same number. So as you can see here, 1, 3, 2, 4, 1, 3, 2, 4, they can't have same thing. But yes, some resources to learn. I've linked them here. There's the IBM Qiskit textbook, which is where I learned. It's very useful and interactive. There's online courses, which I think are very, very helpful. It's just kind of the best way to learn, especially because it's math heavy. And just get into it, start building, and have some fun. But that's it for today. It might be a little heavy on the content, but yes, quantum computing is very exciting.
Yeah.
That was it in the most simplest sense, and you can use it for so many different things. You just have to do the research. But do we have any questions? I think we're good on time, right?
Yeah, I was just going to say, we're basically, it's 2:10 on the dot, so everyone's probably going to have to make their way to their next session. But Jaimil, are you available after if they can just type in questions like in the chat? Would you be able to answer?
Yeah, that's fine.
Perfect. Hey, thank you guys so much for joining this session. Thanks, Jaimil, again. It was wonderful.
Bye.
Yeah, thank you all so much.
Bye. So much. Bye. Thank you.
Bye.
You should have people joining your second. So you can just reset.
Okay.
Yeah, the second group should be joining shortly, but that was really good actually. Very interesting. I really like the program you used. I like how it showed in the sphere. That was really cool.
Yeah.
Yeah.
Yeah. Sorry, go on.
Go ahead. I was surprised that they were all middle school, so I was like, okay, I'll tone it down